Hello everyone, welcome to this new episode of the Brainpan challenge. This time we're going to finally get that remote code execution by exploiting the buffer overflow vulnerability. If you're interested in learning more about these techniques, if you are interested in pursuing an ethical hacker career, then I encourage you to head over to academy.thehackerish.com. There you will find online courses that you can enroll to and just find a suitable course for you. It should give you a great start. This is how the memory is laid out. So we send a bunch of A's like this. So we sent a bunch of A's which have filled the buffer. We overflowed it and found exactly where the EIP is located. And we put here a dummy value. And then we knew that ESP is pointed at the beginning of the string that starts with C's. So the idea to exploit this buffer overflow to get a remote code execution is to populate this EIP with the address where ESP points to. And so once our payload hits the process, EIP will point to ESP, and then the program will continue by running our own injected shellcode. So that's the idea. Now, you might ask, well, how can we find where ESP is pointing to? The answer is by looking for a command that says, hey, just go to wherever ESP is pointing to. And this is called jump ESP. So to show you what I'm talking about, I'm going to find a mnemonic to opcode. So I'm going to use the diffuse.ca website, and here it says enter the assembly code using the Intel syntax. So I'm going to choose, well, I want jump ESP command. Give me its assembly or opcode. I'm going to choose the x86 architecture because that's where Brainpan executable was compiled. And here we can see that jump ESP corresponds to FFE4. So we just want to find a memory that's pointing to FFE4 and put it inside EIP. So once again, I'm going to go back to Ghidra and try to find that exact memory. I'm going to go to search and then for instruction patterns and enter bytes manually. I want to look for the hex FFE4. Apply. So I'm going to click on search all. And here it is. This is our memory. So we're going to copy this value and put it inside our exploit program. Well, it's just a Python line, not really a program. So remember, these B's would be now replaced by our value of the memory that's pointing to jump ESP. But remember, because this is little endian, we need to actually inverse the bytes. So F3 would be the first one, and then 12, and then 17 and 31. So I'm going to use that. So to force Python to represent this as a hex string, I'm going to prepend anti/x or whatever you call it. And then after that, if you understand endianness now, you sure know that it should be 12, then 17, then 31. And let me just get rid of those. Okay, so if our analysis is correct, we should see this value inside our EIP once we run this attack. So let's verify it. Open the Brainpan process and make sure that it's waiting for connections. Run our exploit. Okay. And EIP, now it doesn't point anymore to whatever value we provided it, BBBB, but now it's actually pointing to C's, the bunch of strings which are nothing but the remaining part, which is the string pointed to by ESP. So if we have valid shellcode here, the program would think that it's running something benign, but it's actually our injected shellcode. So now the question is, how do we generate that shellcode? Well, we can turn back to our Kali box and use msfvenom. So that would be msfvenom. We want a reverse shell for Windows, so I'm not sure how to write it, but there is a -L option for payloads, and then we can grep only Windows, and from there we can also grep reverse TCP. Actually, we want stageless payload because we want to listen only using netcat, so I'm going to use shell reverse TCP in the second grep. We'll wait for a while to get the payloads that we need to use for our use case, and hopefully we will find something. Well, isn't that frustrating? Why should I wait for just the name of the payload to use? Well, I guess that's what real hacking is. Waiting, doing a bunch of failed attempts, a lot of stress. It's nothing like the Hollywood movies, isn't it? Okay, finally. So the one I'm going to go after is this one. Why? Because it's 32-bit shellcode and it's stageless and it's for Windows. So msfvenom, please give me a payload for Windows 32-bit shellcode, verse shell TCP. I want the L host to be local host because I'm going to run it directly on my own box, and the local port, well, let's just call it 4444, and I'm going to output it to a file called shellcode.bin for binary. Let's hope that it works. Oh, I made a typo here. It should be equal. lhost equals localhost. Run it once more. Wait for a second or two, maybe 3. Okay, maybe for a while. This is a different machine. I'm going to just copy it over to my Ubuntu machine on localhost. So what I'm going to do is cat that shellcode. As you can see, it's binary, so I'm going to pipe it to base 64 without new lines. Base 64. And I'm going to copy this shellcode into Ubuntu local machine. So echo-n to remove new lines. Not C's. I don't want C's. I actually want this string right here. And I want to base64 decode it and put it in my file called shellcode.bin. Now, if we hex dump that shellcode just to make sure that it hasn't been altered during the copy, it starts with FCE8 and then finishes with FFD5. Yeah, FFD5, FCE8. So our shellcode has been copied properly. So now what we can do is, instead of those C's, we want to actually put our shellcode. So I'm going to put it inside this variable called sc. Well, actually, let me just go back to our previous command. So sc would be here. I'm going to write my exploit inline, but you can surely create elegant Python script to automate that. I leave this as an exercise to you guys. So what I'm going to do is open that file. So f open me the shellcode.bin file, which I know is binary, using the RB option. And then in the shellcode variable, I'm going to put the content of that file using the f.read, the read function. And then I'm going to close the file. And finally, I'm going to send my final string to the vulnerable service. Now, I'm going to add some padding bytes to avoid any execution problems. So I'm going to add maybe 20, 25, something like that, of what we call no operations, or NOPs, just to give some padding and room for my shellcode to execute correctly. Now, if everything goes well, when my script or my service is running, let me just make sure that it's running, I should get a reverse shell. So let's hit that, enter. So it says here, string and integer cannot be concatenated. I certainly just did some typo here. So we opened the SC, we read it, we closed it, and then we printed. Yeah, I just needed to repeat using the multiply operator rather than concatenation, so my bad. Okay, now if we type enter, yes I am, yeah, my bad. I need to prepend these NOP operations before the shellcode, actually, to give it some room. You know, this is how demos work every time. You need to screw at a certain stage. So let me just verify. We have NOP operations, and after that we have the shellcode. Okay, one more time. Maybe this would be the last one. Waiting for connections, and if we hit enter, okay, and the crash seems to be happening between our A's and whatever EIP is pointing to, which is not what we've instructed to point to. So it's kind of weird. Yeah, I think I know what I screwed up. I might need to generate another shellcode. It's containing some null bytes, so I'm going to go back to my Kali box and then generate another shellcode.bin, and I'm actually going to skip any bad characters. such as the null terminating string, or any carriage return, or line feed 0D 0A, and let's retry once more. We need to listen on port 4444. So let me just do that real quick. So that would be netcat-vlp 4444. We're now listening. Let's try. And we get a prompt here, which means that we successfully gained a remote code execution using our buffer overflow vulnerability. In the next video, we're going to actually reuse the knowledge that we've gained now, reuse our exploit, modify it, and make it so that it works on the remote box in order to get remote code execution on it. Until next time, stay curious, keep learning, and go find some bugs.